Over the past 15 years, China has launched more robotic spacecraft to the moon than any other nation. This orbital campaign spans a full decade and a half. Engineers avoided random probes. Orbiters, surface landers, and rovers deployed in a strict sequence. One mission successfully extracted lunar soil from unexplored impact zones. Those rock samples safely returned to our planet. The delivery marked a major technical milestone. Why is this program increasingly focused on permanently shadowed craters? The target is not prestige. Mission planners hunt for ancient frozen elements concealed beneath the regolith. Temperatures inside these polar sinkholes plummet below -200 degrees Celsius. The lunar South Pole features dozens of these deep depressions. Sunlight has not touched the rocky bottom of these basins for eons. Total darkness preserves the environment. The frozen water ice and trapped volatile chemicals hidden here date back over 3 billion years. To locate these ancient resources, engineers in the early 2000s approved a strict 4-phase protocol. They deliberately rejected immediate landing attempts. Instead, they demanded a methodical sequence. First, achieve lunar orbit and map the terrain. Second, execute a physical soft landing on the regolith. Third, extract and return soil samples to Earth. Fourth, construct a permanent base. Each phase required the successful execution of the previous one. The timeline advanced step by step, allowing 0 skipped procedures, 0 rushed launch windows. The execution of the first phase began in 2007. The Chang'e 1 probe launched toward the moon. It established a stable circular orbit at an altitude of approximately 200 kilometers. Operating high above the Great Plains, the spacecraft initiated a continuous scan of the desolate surface. Stereo cameras and altimeters worked simultaneously. Lasers mapped the hidden depressions. Sensors captured the returning signals and transmitted them back to Earth. The probe transformed raw telemetry into complete 3-dimensional elevation models. Mission Control prioritized comprehensive mapping over a quick landing event. They required precise topography to avoid catastrophic surface impacts. 3 years later, in 2010, the Chang'e 2 spacecraft arrived to refine this data. The resolution of the newly transmitted images spiked dramatically. Optical sensors captured the razor-sharp edges of impact craters. Jagged volcanic ridges and deep shadow zones became intensely clear on the control room monitors. The high contrast highlighted every hazardous anomaly. These orbital probes systematically exposed the harsh structural reality of the lunar surface. They identified treacherous slopes and fields of boulders hiding beneath the fine dust. The mapping phase concluded without a single surface touch. Ground stations received these high-resolution topographic maps. Analysts fed the visual coordinates into trajectory computers to calculate a precise, safe landing point for the next heavy rover. Relying on that fresh topological data, the Flight Control Center initiated the surface operation. In 2013, the Chang'e 3 spacecraft descended onto the designated target zone. This event marked the first soft landing on the lunar surface in 40 years. The landing module stabilized. The mechanical ramp lowered. The U-2 rover rolled down the incline and transitioned onto the regolith. Its metal wheels pressed deeply into the fine, abrasive gray dust, leaving sharp tracks on a terrain untouched by human engineering since the 1970s. U-2 immediately activated its ground-penetrating radar and alpha particle X-ray spectrometers. The primary target was the exposed volcanic rock lying beneath the superficial dust layer. For decades, global geological models relied on a strictly limited physical dataset. The historic Apollo missions had returned exactly 382 kilograms of lunar soil and rock to Earth. Geologists mapped the moon's entire composition based on this specific collection, assuming it represented a mostly uniform planetary structure. Furthermore, the vast majority of those historical samples originated from a few selected equatorial zones. The scientific consensus rested entirely on that single regional mineral profile. Then U-2 scanned the basalts in the Mare Imbrium Basin. The onboard instruments detected a chemical signature that directly contradicted the established baseline. It was an unrecognized type of volcanic rock. The mineral matrix held a distinct intermediate concentration of titanium dioxide and iron oxide. This specific chemical profile did not exist within the 382 kilograms of the Apollo archives. The contrast between the two datasets was stark. The 20th century geological models were proven incomplete. The moon was not a static, homogeneous mass of rock orbiting the Earth. It possessed a highly complex volcanic history, where different regions cooled and crystallized under varied chemical conditions across different eras. eras. The historical equatorial samples represented only a narrow, localized fraction of the total lunar crust. U2's on-site material analysis demonstrated that vast geological diversity remained hidden just beneath the surface layer. The mineral composition shifted dramatically depending on the specific impact basin and the cooling rate of ancient lava flows. The established maps covered only isolated patches of the landscape. Beyond those few documented landing sites stretched millions of square kilometers of completely unexamined territory surrounding the lunar equator. To push beyond those newly mapped equatorial regions and reach the uncharted far side, engineers first needed to overcome total radio silence. A spacecraft descending onto the hidden hemisphere permanently loses direct line of sight with our planet. This physical geometry blocks any possibility of transmitting commands or receiving telemetry data. Ground control remains completely blind during the most critical phases of atmospheric free descent. Plunging into this void meant attempting a landing with zero real-time oversight. China resolved this navigational impasse through a methodical orbital preparation process. Before dispatching the exploration vehicle, mission planners launched a relay satellite named Queiqiao. Positioned near the Earth-Moon Lagrange Point 2, this station hovers roughly 65,000 kilometers beyond the lunar surface. From this gravitational vantage point, the satellite continuously monitors terrestrial control centers and the desolate far side. Data signals now bounce through this orbital node, bending communication pathways around the solid mass of the moon. With this communication architecture securely established, the Chang'e 4 mission initiated its descent in 2019. The target location was the South Pole Aitken Basin, an enormous depression scarred into the southern hemisphere. The physical dimensions of this ancient impact zone challenge ordinary terrestrial scaling. Spanning 2,500 kilometers across, this single continuous crater roughly covers an area equal to Western Europe. It remains classified as one of the oldest known impact structures documented across the solar system. Planetary researchers calculated that the original strike responsible for creating this basin shattered the outer lunar crust. The immense kinetic energy punched a hole straight through the protective geological layers. This violent excavation process exposed ancient rocky material previously buried deep inside the mantle. Overcoming the communication blackout, the robotic lander finally secured its mechanical footing directly upon these excavated rocks. Securing that remote surface foothold was merely the opening operational gambit. In 2024, the Chang'e 6 mission drastically escalated the timeline. The robotic probe scooped roughly 2 kilograms of pristine far-side regolith. After sealing the ancient soil, a miniature ascent module ignited its engines. It blasted off the silent crust and achieved orbit over the hidden hemisphere. An automated rendezvous vehicle intercepted the ascending module high above the craters. It secured the cargo and initiated the long journey back toward Earth. Every single mechanical stage required flawless execution without human intervention. The recovered fragments proved to be 2.8 billion years old. They displayed unmistakable chemical signatures of unexpectedly late volcanic activity. Textbooks changed immediately. The lunar interior had clearly remained violently active much longer than previous theories allowed. Yet these profound scientific discoveries cleverly obscure a much deeper strategic intention. Complex sample returns act as demanding dress rehearsals for future heavy infrastructure. The true prize lies elsewhere. Beijing currently targets a completely different operational zone for its primary base. The intended destination is the lunar South Pole. It is a territory defined by sharp physical extremes. Because the lunar axis maintains almost zero tilt, solar radiation approaches this hemisphere at a shallow angle. The sunlight merely skims the horizon. It illuminates only the highest ridgelines, projecting vast shadows across the deep valleys below. The true anomaly exists within the deep impact craters dotting this southern landscape. The towering rims of these geological depressions rise high enough to block incoming solar rays. Consequently, the rocky floors of these basins remain locked in permanent shadow. Researchers confirm that several of these deep cavities have existed in total darkness for over 1 billion years. They remain untouched by a single photon since long before complex organisms evolved on our planet. Inside these permanently shadowed regions, thermal sensors register -200 degrees Celsius. This localized environment plunges to temperatures colder than the remote surface of Pluto. It creates one of the most extreme natural deep freezes identified in our solar system. This severe thermal drop creates a unique geological trap. Over billions of years, countless comets and asteroids bombarded the lunar crust. They carried trace amounts of moisture to the surface. Incoming water vapor quickly evaporated across the sunlit equatorial plains. However, any molecules drifting into these dark southern craters froze instantly upon contact. Shielded from solar degradation, these thick deposits of water ice sit perfectly preserved within the regolith. Now, this ancient frozen reservoir transforms a desolate crater floor into the most critical strategic objective beyond Earth orbit. Accessing those preserved ice deposits unlocks much more than drinking water for a lunar base. The chemical composition of water provides oxygen for human respiration and hydrogen for propellant. Subjecting that frozen material to electrolysis yields supercooled liquid hydrogen, ranking among the most efficient rocket fuels available. Operating a spacecraft launch facility on the lunar surface bypasses the steep financial penalties of terrestrial physics. Gravity dictates the price. Lifting heavy payloads off our home planet demands massive booster stages to reach low orbital altitudes. The lunar environment offers a surface gravity equal to approximately 1/6 of our terrestrial standard. Escaping that weaker pull requires only a fraction of the thrust compared to ground launches. Deep space trajectories targeting the Martian surface or the Jovian moons could utilize this location to replenish propellant tanks. The first nation to establish this extraction infrastructure will control the primary supply chain for deep space exploration. This strategic advantage explains why the Chinese lunar program focuses on securing a permanent presence at the southern pole. Controlling that primary supply chain demands hard physical evidence, not orbital estimations. You cannot just circle above the polar darkness and hope the sensors read correctly. You must enter the abyss. Normal surface rovers rely entirely on solar panels. Darkness means immediate power failure. Their standard wheels cannot survive the jagged, deeply fractured terrain inside a crater untouched by sunlight for over 1 billion years. China answered this severe engineering limitation with the Chang'e 7 mission. Scheduled for launch in 2026, it represents the most technically ambitious lunar operation China has ever attempted. The mission introduces a mechanical concept never before deployed in the history of lunar exploration: a small, autonomous robot designed to jump. Instead of slowly rolling across hazardous ground, this hopping probe leaps directly into the permanently shadowed craters. It carries highly specialized instruments designed to detect water molecules and sniff out subtle hydrogen signatures. It actively analyzes frozen chemical deposits buried deep within the regolith. The machine enters the crushing darkness, executes its analysis, and extracts itself from environments that would destroy a standard rover within minutes. Nimble and fast, it navigates areas where nothing else can survive. The full Chang'e 7 architecture extends far beyond this single hopper. A dedicated orbiter circles the southern polar region, mapping the rugged terrain and maintaining a continuous communication relay with mission control. A heavily instrumented lander touches down on stable, illuminated ground near the polar edge. From this secure base, a traditional wheeled rover deploys across the surface to scout optimal target zones for the jumping probe. These 4 distinct components operate together as a single coordinated network, constantly feeding critical telemetry back to scientists on Earth. If Chang'e 7 confirms massive water ice deposits hidden inside those ancient craters, the discovery alters the trajectory of space exploration. It proves the fundamental resources required to sustain permanent human expansion are already waiting on the surface, billions of years old and perfectly preserved in the dark. This hidden water represents just the first phase of the operation. Locating the hidden ice opens the door for the next logical phase: constructing infrastructure directly from lunar regolith. Shipping heavy concrete and steel across 383,000 kilometers of empty space is logistically impossible. Therefore, the fine gray dust covering the lunar surface becomes the primary building material for any long-term presence. Converting loose dirt into stable architecture requires navigating extreme physical parameters. The lunar equator experiences severe temperature fluctuations, shifting from a blistering 120 degrees Celsius during the day down to minus 130 degrees Celsius at night. The environment features constant radiation and pervasive, highly abrasive dust. This fine powder clings to surfaces and easily wedges into the mechanical seams of moving parts. The upcoming Chang'e 8 mission, scheduled for approximately 2029, focuses specifically on solving these material challenges. The mission serves as a testing ground for in-situ resource utilization. Instead of transporting modules from Earth, the objective is to manufacture components entirely out of local minerals. One major experiment involves gathering the loose gray regolith, then applying intense heat and pressure to compress it into solid, durable bricks. These dense blocks provide the foundation for robust landing pads, which will prevent descending rockets from kicking up hazardous clouds of debris. They also serve as heavy radiation shields and paved pathways for utility rovers. Beyond basic structural elements, the regolith contains another critical resource. Lunar rocks hold high concentrations of oxygen, chemically locked within solid mineral compounds rather than floating as a free gas. Specialized extraction equipment will attempt to break these stubborn chemical bonds through high-temperature processing, releasing breathable oxygen directly from the crushed rock. The ultimate application of this material science relies on automated three-dimensional printing technology. Robotic units collect the processed lunar dust, melting it and extruding the molten material to slowly construct large-scale architecture. The machines deposit the material layer by layer, building from the ground up without human intervention. This method allows for the creation of complex geometries designed to withstand the vacuum of space. Autonomous printers systematically erect thick walls, paved floors, and curved protective domes long before any human crew arrives to inhabit them. Once the printing technology passes its final trials around 2029, the timeline accelerates into a major construction phase. The early 2030s mark the official assembly of the International Lunar Research Station. This massive undertaking focuses heavily on the lunar South Pole. Certain geographic features make this specific location highly strategic. Craters like Shackleton contain elevated rims known as peaks of eternal light. These ridges remain constantly bathed in sunlight. They provide continuous solar energy for a permanent outpost. Robotic operations initiate the primary deployment sequence. Cargo landers methodically deliver heavy power generation units directly to the surface. Communication towers and modular scientific laboratories follow closely behind. Machines handle the most dangerous assembly tasks in complete isolation. They establish the critical life support infrastructure long before human crews prepare for launch. The station expands module by module through a carefully orchestrated automated process. China positions this expanding lunar footprint as an open platform. The initiative rapidly gains international momentum. Dozens of nations are officially committing resources to the project. They plan to contribute scientific payloads, specialized technology, and future personnel. Multiple countries utilize the established Chinese foundation to secure their own permanent presence on the moon. While robotic systems prepare those landing zones for the international coalition, engineers on Earth rigorously test the heavy transport architecture designed for human crews. Initial crewed visits span only a few brief days. These short preliminary flights contrast sharply with the ultimate objective of establishing a permanent and self-sustaining infrastructure across the lunar South Pole. The Chang'e spacecraft undergoes abort tests in 2026. This proves strict safety protocols. At the core of this massive logistical network stands the Long March 10 rocket, a heavy-lift vehicle engineered specifically to carry unprecedented payloads into orbit. Executing one expedition dictates overwhelming industrial scale. Assembling a single lunar mission demands a massive numerical commitment, requiring two separate 27,000-kilogram launches to construct one complete flight profile. The moon does not represent the final planetary destination. It is a necessary logistical springboard for navigating the broader solar system and expanding human reach. Its surface gravity measures roughly 16% of the pull experienced on Earth. This fundamental physical advantage drastically reduces the fuel required to launch subsequent heavy vessels deep into uncharted space. The unique far side guarantees complete radio silence. Meanwhile, local resource extraction promises the necessary propellant for extended onward journeys toward distant planets. The first coalition to construct lasting operational infrastructure on the lunar surface establishes the exact terms for how all future interplanetary missions are planned and executed. This synchronized megaproject transforms a barren rock. It systematically turns a desolate celestial body into a strategic outpost for long-term human expansion across the cosmos. This precise transportation sequence abandons traditional single-launch methods. It relies entirely on an unforgiving dual rocket architecture to achieve its ambitious goals and ensure crew survival. One heavy launch vehicle carries the astronaut crew securely inside their specialized orbital spacecraft. The second identical rocket transports the heavy lunar lander itself. Both components navigate the dark void. They travel independently before initiating a highly complex rendezvous maneuver high above the shadowed polar craters. Two independent rockets dock silently in lunar orbit, completing the final spacecraft assembly for the descent to the surface.